So, how's homework going? Does anyone have questions that they want to talk about for homework? Is it because you don't have questions because you've got it under control, or you haven't opened it yet and you don't have questions? Guilty smiles. Okay, it's the latter. That's fine. That's fine. You got a week and a day to get it together. There's only 3 models. It's actually not that bad. Let me know if you have questions. I have office hours as well today, so we'll set that aside. Let's see, what else? What do we have to do? What's left? 3-level stuff, right? That's where we were. Nobody wants cupcakes? Like, seriously, I cannot take home 40 cupcakes. That's just not going to happen. Please come have some cupcakes. And someone else brought candy canes too. That wasn't me, but there were candy canes back there a while ago. Let's see. We want that one, and we want longitudinal twin models. So yes, we are looking at empty models and ICCs. It's okay. Take another one.
What the?
See, that makes me very sad that the frosting is wasted. I probably would have licked it off the table.
Oh, I'm sorry. I didn't mean that.
That's the best part, right? Anywho. So while you guys are getting some snacks, should we pull this up? Talk about 3-level models? You came, right? You must want to talk about something. Or at least some of you came, let's put it that way. The late in the semester attendance rate usually decreases, but that's okay. All right, so we looked at 2-level models and 3-level models, right? So the setup for this is time at level 1, nested in person at level 2, who is nested in twin pair or family at level 3. So that requires 2 different kinds of ID variables in the data set that I'm working with here. These are real data, so I can't give them to you. Pair ID denotes which family is which, and twin ID is just 1, 2, 1, 2, 1, 2. So this combination right here gives me the unique identifier without actually having to make that variable. Stata would not use that trick, so I had case. So we started with a 2-level empty model for time within person that ignores the dependency of persons from the same twin pair, so assumes persons are independent. So it's not a good model, but it's a jumping off point. Found that the intra-class correlation for that 2-level model was 0.85. Do you remember what that means? In this context, we've got time within person. So 85% of my variance is what? The answer is always between. The question is between something, right? It's level 2, which means between, and in this context of time within person, it is. This is just a 2-level model right now. So this is the very first model, ignoring family for right now. So this is time within person as my 2 levels. So 85% of my variance in this outcome is between what? Persons. Good. Said differently, 85% of the variation is because some people do better on this test on average. Said differently, 85% of this longitudinal outcome variation is actually cross-sectional. You can say all 3 of those things. The average correlation of occasions from the same person is 0.85. So in that sense, it's interpreted as a true correlation. Then we added a 3rd level. So in terms of the equation, that requires 3 levels of equations, 2 different placeholders. So we have beta 0 as my level 2 placeholder. That level 2 placeholder is then defined in the level 2 model by a level 3 placeholder, which is this delta thingy here. And then finally at level 3, how each family gets its own mean starts off with my fixed effect for the intercept here, gamma 0, 0, 0, plus my random intercept deviation for that specific family. Those things combine to come back to level 2, pick up U0, which is how far off I am from the average of me and my twin. So within twin differences. And then that comes down to level 1, and we pick up E, which is how far off my predicted mean is from the actual occasion's outcome. So to do this in SAS, I do not believe it matters which random statement you write first. I think it just only matters which identifier you have. That's how you know what level of the model it is. I just start with the highest level written first as just a convention. In Stata, that is not the case. So in Stata, the highest level has to be first. It assumes that anything after that is nested within it. And you also have to specify this covariance unstructured at each level, otherwise the default is that it does not put a covariance between your random effects at the same level. And we don't want that. So we now have 3 different piles of variance, level 3, level 2, level 1. Because they're orthogonal, we can sum them up, and to do that, to create a proportion of variance at each level. So 54% of the total variance was level 3 between pairs. 31% was, you can either think of it as between person or within pair. Those mean the same thing in this context. I like to think of it as within pair. And 15% is within person at level 1. So then there's 2 different kinds of ICCs that would be useful here, in my humble opinion. One of them is the level 2 ICC, which is 0.85, the same as the previous model. Not a coincidence, right? It's the same information. Because what happened previously is that level 2 and level 3 were just smushed together. What I was calling level 2 was actually 3 was embedded in it. So in terms of the formula, the numerator here explicitly separates 3 from 2 because that's how the model operates, but the previous model did the same thing. It smushed 3 and 2 together by not having a third level. Sure.
So here when you just longitudinal data, we say that it is between person, is it over time or the mean difference? So what is the difference between these?
Homework question. So between persons is not over time. Between persons is on average. Within persons in this design is over time. And that's because the same people are measured repeatedly. That's what makes time level 1 in this particular case. Time is not always level 1. It depends on the design. So in this case, because people are measured repeatedly, level 1 is over time. Level 1 is the longitudinal part. Level 2 is the person part, and it's an average across time at this point because we don't have time in the model yet. And so this is the proportion of variance that is between persons on average. It's aggregated over time. In other words, if this was not a longitudinal study, then we would have 85% of the information still. We gained 15% of the information by repeating this measurement 4 times, or having 4 occasions. So this is the part that's cross-sectional, that is between persons on average, not over time. The time part is the remainder, 15%. That help?
Yes.
Okay, more question. All right, then this one. The goal of ICC level 3 is to take that between person level 2 and above variation and split it into how much is 3 versus 2. So the numerator of ICC level 2, which is the level 3 random intercept variance and the level 2 random intercept variance, that term becomes the denominator for ICC level 3. So of this 85% as my new baseline, how much of it is actually because of between family level 3 random intercept mean differences? And the answer is 64%. So 64% of the 85% is what that means. The other way that you can think about what the 64% means is to think about what it would be if people were independent. If people were truly independent and we didn't need level 3 in the model, what would that number become? It'd be 0. So this is an effect size for whether or not you need a level 3 random intercept variance in your model. To do a significance test to go with that effect size, you can consult the likelihood ratio test. The little macro that I wrote spits out this output above. So the fact that the -2 log likelihood went down by 111 after adding the level 3 random intercept variance, that's significant. That means it made the model fit better. 0.64 is the effect size that goes with that idea. How much of the level 2 and above variance is actually level 3? It's 0.64. And if the twin people were automaton robots who are exactly the same as each other, what would that number become? It'd be 1. So if people are completely independent, the level 3 ICC would be 0. If people are exactly the same, it would be 1. There are other variants of ICCs that can be more useful in different kinds of designs. So as a general recommendation, give people this information specifically and give it to them first. Because if you know what proportion of variance is at each level, you can make these into whatever ratios you feel are useful. As a side note, what Stata gives if you ask for the STAT ICC command and what M+ gives in a 3-level model is this right here as the level 3 ICC. So that is 3 over total. That gives you the expected correlation of occasions from the same family, not necessarily the same person. I don't know why that would be useful in life, but in certain kinds of designs it could be. So, but it's not the same as this one right here. So, okay. How are we doing? You're starting to look very sad. You need more cupcakes? Because no judgment, right? I figured out that if everyone came and everyone took a cupcake, that we would have enough for like 1.5 cupcakes per person. But as you can see, not everyone came, so you can each have like 3. Because I have to carry these all the way back to the parking lot if you don't eat them. Or maybe I should stick them upstairs in the grad lounge area, right? That's a better choice? I think so. Because I don't need like 50 cupcakes at home. Nothing good can come of that, right? All right, so this is what we did right before we left last time, is do the same empty model partitioning of variance for our age as a level 1 predictor. So this particular design, let me go back to the descriptives here at the very first page. This is what's known as an accelerated longitudinal design. Synonyms for this, cohort sequential design, overlapping cohort design. Accelerated, I think, is the most common, but there's others. Basically what that means is that you are trying to cheat your way into a longer longitudinal study than you actually have. So if I have a 21-year age spread at the beginning, and I follow everybody for up to 6 years, in this example I used 4 occasions, then in theory I have a 27-year age spread, even though not a single person was observed for 27 years. So these sorts of designs are banking on the idea that people are more or less interchangeable, and that you could look at like an age trend over 27 years by cheating your way into the design like that. Unfortunately, in this context especially, that isn't going to work. Now let's think about selection and attrition, right? Who is able to sign up and participate in a research study at 100 years of age? Is that a random subsample of the population, do you think? No, those are the super seniors, right? They are like superhero level with it to be able to do this. So if you think about this from a selection point of view, the people who are still around at 100 are not a random subsample of all possible people. So you can't think about this trajectory as going from 79 to 106 because it's like lumping different kinds of people together. Plus, what happens to people who don't complete all the occasions, right? Attrition. In this case, probably due to mortality. Then you simultaneously have sort of the people who are probably doing the worst dropping off and the people who are doing the worst not joining in. So it's this hodgepodge of different times and people that prevent this from being just a simple time. So that was one of the reasons I wanted to show this to you, is because it contrasts with like what you're doing in your homework, for instance. In your homework, you have a program over 9 weeks, right? Everybody is starting the program at the same time and they're being measured on the same schedule. So in that context for your homework, time is completely within persons. The ICC for time would be 0 in a 2-level model. It's not in this case. Yeah.
Related to that, since we have two, this was one of my questions, but I didn't want to ask it because I thought I knew the answer, or I don't know. But, so yesterday you mentioned centering, we have to subtract 1, but why did you subtract 1 from week if you want it to be at 0, but there's 9 weeks? And like, are you supposed to, I'm assuming it was supposed to be the mean, right? Is that just given to us?
Not the mean. I wanted you to center such that week 1 became time 0.
Oh, that's why, okay.
Mm-hmm. It's otherwise, like if you left week alone, your intercept would be the expected outcome the time before the study started, which is not wrong, but it's weird. So generally speaking, you want to center time so that 0 is somewhere within the span of time observed. It would have been just fine to center at time 5 as the middle, and then your intercept would be the expected outcome halfway through the study. Or if you centered it at 9, your intercept is the end, which if you're focused on sort of how effective the program ends up being, would be a reasonable thing, because then the program main effect would be at the end and not the beginning. So, but yeah, you just subtract 1, that's it. But in this case, because we have this cross-sectional variation at the beginning, we have to worry about smushing age. That's what it boils down to. By the way, I got a free trip to Europe for knowing this. No, I'm not. I'm dead serious. In 2012, maybe 13. It was a while ago. I wasn't a parent yet, which is why I got to go. I got an email from Joop Hawks. Do you know this person? He's like a god in multi-level modeling. He's in the Netherlands at a university in Utrecht. And he was doing a multi-level modeling conference, and he wanted me to come and give a talk about that. And I said, yeah. So we went to Utrecht, and I did the talk, and we went to Paris on the way, and we were in Amsterdam for like 5 minutes. And so, yeah, I got a free trip to Europe. So this stuff matters, right? And on a practical level. I was curious as to how, like, he found, like, found my stuff actually. And when he introduced me, do you know what he said? This is one of the coolest compliments I've ever gotten. He said, I had to teach a course on growth modeling and longitudinal analysis, and I hadn't done it before, so I started Googling for course examples, and her course came up. And he liked the stuff enough to come invite me to give a talk at Utrecht. So it's cool. Yeah, I've also been on free trips to Australia, and I've been to Sweden twice to give workshops. Not only free, but they paid me to go there. So you learn this stuff, you'll get to tour the world for free. Anywho, yeah. So age is smushed if we just put age in the model. So I'm going to show you a specification that unsmushes it. Because the strategy I'm going to use is different than using person mean centering or group mean centering. So first step then in figuring out how to handle age is to determine at what levels it has variance. So because people were sampled longitudinally, we expect level 1 to have variability in age, and it does. Because these twin pairs were ages 79 to 100 at the beginning, we expect age to have variance that's cross-sectional, and it does. And all of the variance is at level 3 because that's what being a twin means. Right? People are the same age within the group. So that means that in this model, I need to have some version of age represented at level 3, and I need to have some version of age represented at level 1. So I'm going to use a different type of centering. Rather than mean centering, I'm going to use something called baseline centering. I would argue in this context, it makes more sense. So the way that it works, here's the data manipulation that's required. I am taking their age at wave 1. So age has been saved to a data set where I have their wave 1 age, wave 2, wave 3, wave 4, and I also have a stacked data set. Their age at the first occasion is going to be my level 2 predictor. I'm centering it at 85, which was near the mean for the sample. My level 1 predictor, what I'm calling time, is their current age at each occasion minus the age they were when they walked in the door at wave 1. So you can think of time as time passed since the study started, and their age that they were when the study started is going to go in here at level 3. So I have between family, age 85 is the name of the variable. Now, why did I do it this way, you might be wondering? Any guesses? Why not do a person's mean age and stick that in the model at the higher level instead? Because that's what we did all semester, right? We took the group's mean, stuck it in the model. Last semester, we took no, I guess we didn't do that last semester. Take that back. We did it at the very end. We took the person's mean and did the same thing.
Does it have something to do with the fact that they're twins and their ages?
In this case, no. I would do the same strategy if these were just singleton people. They can't survive for that long. Can you say that a little more positively? Yeah, it's because they die. That's why I did it this way. You're not wrong. But yeah, so if I want to think about like what is a person's mean age, it's a function of two things: how old they were when they started and whether or not they completed all the occasions. So a mean age is going to be biased downward if people die and don't come back, or if they don't come back for any reason, right? So rather than have a mean age that reflects both cohort differences, as it's called, and the time in study, I chose just to do cohort. So their age at the beginning allows me to look at what the cross-sectional effect of age is. What is the effect of being a year older when you walk in the door? That's the version that I would get if this weren't a longitudinal study and I just grabbed a bunch of people of different ages and I put age in the model as a predictor. So between family age 85 is going to carry the cross-sectional effect of being older when you start the study. Level 1 time is going to carry the longitudinal effect of getting older during the study. Being older, age differences, versus getting older, age changes. Two different things.
So I have a question.
Yeah.
So given this study, some people, they just cannot make it that long.
Yep, that's true.
And if I don't think in that way, the time they disappear is kind of like missing data.
It is missing.
It's not missing at random. It's like for sure. I don't know, like if you treat them as, see it from the missing data perspective, so that's not like a tactable or like a doable thing to address.
So your question is, how are you assuming missing at random, right? If these people are not coming back because they're dying. Is that the question? It's a good question. There's good news and there's bad news. Is missing at random, so let's define that. What does missing at random mean? Because it doesn't actually mean random. It's one of those confusing phrases. Random is if it's missing completely at random. Like the missing data has nothing to do with what the values would have been. It's just totally random. Like if you're giving a survey and the copy machine eats one of the pages for some people and they don't get those questions. Has nothing to do with what they would have said. That's missing completely at random. Missing at random is conditional random, right? It's random conditioning on the rest of the person's information in the model, their predictor values and their other outcomes. So what maximum likelihood estimation tries to do is to create model parameters that would have resulted if the data were complete. The assumption is that whatever multidimensional likelihood function each person has from their outcomes, the shape of it, would be the same if there were more points in it. That what they have is accurate. So from the perspective of the people who die sooner probably were doing worse, like either they had a steeper trajectory falling down or they may have been lower to start with. If we have at least some of their data in the model that captures that, then that helps to satisfy the conditional random idea. But let's say that reviewer 3 brings this up and reviewer 3 wants you to test for missing at random. What do you say?
Thank you, and then you address it.
Thank you for that insightful comment. However, and we'll have to figure out how to spell this, neener, 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 because missing at random is not testable. You, by definition, you don't have the data to test it. It's missing. Question?
Yeah, so you mentioned that we're not subtracting the mean as we had before because they simply don't all last that long. But if you did a study where you had a high dropout rate, so would it hold there as well? You wouldn't subtract the mean, you would subtract something else?
It depends on the context. Like what I'm trying to do is capture directly the two sources of age variation that were introduced in the design. There's the design, by sampling people of different ages at the beginning, we've introduced cross-sectional variation, and this age at wave 1 predictor captures that directly. A mean across time would capture that directly if you had complete data. It'd be one and the same. But if you don't have complete data, that mean is going to be a function of attrition and cross-sectional age differences. So if you're concerned about missing data that is missing not at random, which is the bad kind, meaning that it really has a pattern and you don't have enough information to detect it, the only thing you can do in those sorts of models is run models under some sort of specified mechanism for what the missingness, how it was generated. Like they call it like a sensitivity analysis. Like if the missingness was caused by this, I need to somehow figure out a way to operationalize that and stick it in the model and then see how the results differ across various versions of that. A simple way to do that is to put in the number of occasions they completed as a covariate. So you could see our outcomes at the first occasion lower for people who are going to drop out than people who stay the whole time, because that helps to satisfy missing at random, the more pieces of information. Similarly, if they dropped out because they moved versus they died, right, that's a covariate that could go in the model and help satisfy conditional random. Side note, I have never once in my life done multiple imputation. Because if you put the same information into the imputation model that you put into your analysis model, they are asymptotically equivalent. Where imputation comes in handy is if you have missing predictors, because they drop the cases out of the model if you don't have complete cases. So that's where the thing is. But missing outcomes, it's not a problem. It's not solved, let me put it that way. Okay. So another thing I'm doing in here, I'm coding for zygosity, MZs versus DZs, and then because of missing predictors, I am making sure that every case that remains has the variables of interest, which is their age at each occasion, their age at the beginning, and the information test outcome. Everybody in the data set had zygosity already for sure. Okay, so questions on the setup? All right. So yes, we got to keep an eye on the clock here. That way you have time to do your evaluations and eat your cupcakes. So in these models, when you have balanced time, or you can round yourself into a situation in which you have relatively balanced time, getting the model estimated means at each occasion is the step one, because that helps dictate what type of modeling family would be useful for you in terms of capturing the trajectories. So to do that, I'm switching over to Glimmix just for this example, because Glimmix has an option on their LS mean statement to make a plot directly. Margins plot in Stata does this all the time, so this is just a SAS limitation that I'm trying to work around. I am using a categorical version of time, which is called wave, so it's just wave 1, 2, 3, 4. By putting it on the class statement, this is fitting what's known as a saturated means model, or one mean for each occasion. And I did that solely just to make this picture. So looking at this picture, does this look straight linear to you? A little bendy, maybe. Bendy being a technical term. So I'm going to go with quadratic-y. Let's start there. So these are my means at each occasion. These are the means that are estimated by the model, trying to capture what the means would be if the data were complete. So if you wanted to report descriptive statistics, report those, because that is what your trajectory is trying to capture, not the real means, which assume missing completely at random instead of missing at random. So here's my model. At level 1, I'm putting in age Tij, so that is level 1 age minus pair age. And I'm putting that in as a linear effect and a quadratic effect, introducing beta 1 and beta 2. Beta 1 and beta 2 then show up in the level 2 model. Right now they only have fixed effects, this just looking at the fixed effects, and then we'll add random effects one at a time. So the level 2 model has delta placeholders for what those effects are going to become at level 3, which then finally are the fixed effects. And because there are so many placeholders in this model, if you give people equations, I would highly recommend labeling them, because otherwise it's like impossible to keep this straight. So throw them a bone and help tell them what the equation is for. In practice, I'm just putting in time and time squared, or time and hashtag time in Stata. My other class made a funny joke. They called this hashtag moderation. Is that funny? No? I thought it was clever. Like, because you know the interaction term is moderation, and this is like hashtag moderation, like, you know, in the Twitter. No? Okay, well, that killed earlier, so I liked it. So what happened after this? So these two fixed effects that we added here, these are level 1 effects of time. So which of my 3 variances should they have reduced? Level 3, level 2, or level 1? Level 1 effects of time should reduce which kind of variance? What? Variance in time, level 1. Yeah. So the empty model, in other words, draws a flat line through the means, right? Intercept-only model. By putting in a quadratic line instead, we should explain some of that level 1e variance. So I could do a pseudo r-square for that, and did. It worked out that we see an 8.3% reduction in the level 1 variance from time, so not a strong effect, but we have enough occasions to make it reasonably significant. So here are my fixed effects. So given my strategy for centering, the intercept is the expected outcome at time 0, which is when the study started. Age is not yet in the model. So it's for anybody. They walk in the door, mean is 26. In looking at the fixed effects here, I've got a negative linear effect of time, that is instantaneous at time 0, and I've got a negative quadratic effect of time. So if you think of time by time as a two-way interaction term, What kind of pattern is this? You've got 4 choices. More positive, more negative, less negative. The quadratic effective time is doing what to the linear effective time in this case? More negative, more downer. They're heading down, and as time goes on, they go down at a steeper rate. However, it looks like these fixed effects are not significant, but they're staying for right now. Now what I'm going to do is add random effects of time, one at a time. And because I knew at this point in the semester we would all have lost our will to live, here, that one. This is the new thing. Rather than playing Where's Waldo with the change in the equation. So we're picking up a level 2 random linear effective time. We are allowing people to have their own rates of decline. So time is going on the person level random statement in SAS. Analogously, it's going after twin ID in Stata. Anytime we add a random thing, how do we know if it helps the model? Likelihood ratio test, or -2 log likelihood difference. Survey says 136 is how much the -2 log likelihood decreased on 2 degrees of freedom. P-value significant to a whole bunch of decimal places, so yeah, that helps. Next one. Random linear time at level 3 also. So we're picking up another V term in the level 3 model. In other words, we're asking, okay, so people need their own linear time slopes. They need their own rates of change. Got it. How much of people need their own change is in common of people from the same twin pair? Are twins related in how much they change over time? So now time is on both lines. Survey says no. So the -2 log likelihood difference is less than 1. Even using a mixture p-value wouldn't have helped that thing. The cutoff for a significance for a mixture p-value of 1 and 2 is 5.14 instead of 5.99. That's still well below it. So no, we don't need the level 3 random slope. I did ICCs for the intercept and for the linear slope out of the output. So what I'm asking is pair level dependency in the trajectory. So of the random intercept variance that is at level 3 and level 2, how much of that is actually level 3? And it's 64%. That's almost identical to what the level 3 ICC was from the empty model. It's the same idea. It's just that this is conditional on time 1 as opposed to on average across time. I did the same thing with the slopes. This is something that we haven't seen before because we've never had random slopes at multiple levels that are hierarchical. So it's the same idea. Out of the total individual differences in change, how much of it is level 3? How much of it is common? And the answer is 7%. The fact that adding a level 3 random time slope variance, this one right here, didn't help the model fit better, the fact that that likelihood ratio test for it was non-significant, means that that 7% ICC for the linear slope variance is basically 0. So to put all of that back together in English, there is strong twin level dependency in where they start. 64% of the intercept variance has to do with which family you're from. There is non-significant twin dependency, pair level dependency in the slope. So twins don't share variance in change. They decline at their own rate. Which makes sense, right? This outcome is a measure of crystallized intelligence. It's like world knowledge and stuff like that. What do you think are factors that contribute to world knowledge? Like education, SES, those kinds of things? Things that the twins would have in common? In this context, what do you think contributes to the decline of crystallized intelligence? Dementia, illness, things that happen to people sort of individually.
So like the intercept is like not like the age when they enter the study.
It's just, at this point, age is not part of the story. It's literally time zero. Whenever they entered.
Yeah, whenever they entered. But like they are like at least like 79 something. Like cause it's like about.
We are ignoring the 79 to 100 age spread at the beginning so far.
Yeah, but still like the range of like age is like 70, almost 59 to 100 something.
79 to 100 at wave 1,
Yeah.
yes.
No, I just thought that it's interesting because like after, so like it means like once they became like older, like how like their like movement, like the trajectory, like like not very matter to the like the fact they are trained. But like before they entered, like cause like they share 64% like intercept part. So like when they are younger, like it means like actually if they are trained or not, it's like a more matter, right?
Say that again?
Like means when they are younger, cause like intercept is like when they are youngest, like with
Yes.
the big set.
Yes, the
Or,
intercept is when they're
When
youngest.
they are younger, like actually like maybe like they are more related to like or like once they became older and older, actually like it doesn't matter if they are twin. Does it?
Yeah, you could think of it that way. So it matters less that they're a twin the older they get. Yeah.
So
Yeah.
I'm just thinking like so it means could be like if you have like data like about like about them like when they are younger, maybe like their trajectory may be more like related. Right? Because like in intercept part like they are sharing, so it means like until like we don't have a data set, but like if we reach that part like no, the time like from age 0 to like our intercept part, like maybe they shared like trajectories more. It's a reason like why they have like pretty high like rate of sharing like variance of intercepts, right? That's it like am I overthinking?
I think you're right. So if we recentered time to where the intercept was the end of the study, I would expect this number to be smaller for the ICC for the intercept. Because yeah, as they grow differently, they will become less related. And so this model, by the way, has gotten a lot of criticism because up to this point, we're ignoring that 79 to 100 spread in age. I'm not going to keep ignoring it because that would be silly, but I'm putting it in as a level 3 predictor where it belongs. So that's next. So we are putting in, again, this one, pair age centered at 85 as a predictor of the intercept and the linear time slope. I'm leaving off random effects for quadratic time for right now. Let me find. Yeah, by the way, after I put all the random effects in, I actually have a significant quadratic effect of time. It wasn't significant before they were there. So, just as an FYI. So yeah, by putting in age, what I'm asking is, do people who started the study older, do they have a different intercept when they walk in the door? And do they change differently too? So this idea that the reason that people are declining is because they're getting older. That's actually a testable hypothesis in this design. Because if that's true, you would expect the people that are the oldest to have the most negative slope. But you could put other variables in here too that differ between people at wave 1 as well. Health variables, education variables, personality variables. You could test all sorts of reasons why some people start out higher and some people change faster. Age is just one of them. So I'm adding in between family age 85 as a moderator of the intercept and slope. It looks like age significantly predicts the intercept. So when you see a main effect of a predictor, think about what it's doing as an intercept-specific effect. It's adjusting the intercept. So as you might expect, for every year older you are when you walk in the door, your performance at that point is lower by 0.86 significantly. And I have a note out to the side here. Because this is a level 3 predictor, it should have accounted for level 3 random intercept variance. We have, did I leave? Yeah, I left the level 3 time slope variance in the model because I wanted to make sure that the effect of age by time was treated correctly. So if I go like this, which pattern is this? So people who are 85 have an instantaneous linear rate of change at time 0 of minus 0.4. For every year older you are when you walk in the door, that rate of change becomes more negative. Yeah. So older people decline faster, non-significantly. It'd be less negative, a lesser rate of decline. And by the way, I once had a student argue with me that like less negative and more positive are the same thing. They're not though, because if you look at the weather on your phone, it says things like, not as cold today. It does, right? It doesn't say warmer, it says not as cold. Yesterday was really effing cold. Today, not as cold. Exactly, it's still cold though, that's the point. It's not warmer. Right? If I'm still wearing snow boots, it is not warmer.
But this change is not significant.
Correct. Unless you want to play fast and loose with p-values. But the pattern is such that older people decline faster. And that should explain the level 3 random linear time slope variance. And actually, it explained 32% of it. So even though the effect is non-significant, it explained a sizable proportion of the level 3 time slope variance because the level 3 time slope variance wasn't significant in the first place. It's easy to get a big pseudo R-square if you don't have a lot of variance to account for. Yeah. So then I threw in zygosity as a predictor of the intercept and slope and its interaction with age. And that was to set up the idea that we're going to look at variance differences by zygosity. So even though you wouldn't expect them to be there, there were a few actually, which were interesting. But here's the new part that I added to this example last time that is specific to the folks who do genetics analyses. This right here. You can do it in SAS and you can do it in Stata. I was never able to get it to work with SPSS. But the idea here on these group equals, and by estimating random intercept and slope variances in Stata that are MZ-DZ specific, you are allowing different random intercept and time slope variances by zygosity. So if genetics matters, there should be more commonality between twins who are MZ than DZ. And so this is what's necessary to be able to piece apart how much of the shared variance is genetics versus environment in these models. So we do a likelihood ratio test to see if it fit better, and it did. And so then I ended up with these things right here. So if you're interested in heritability analyses, there you go. That's how I was able to use these models to calculate percent of variance that's due to heritability, common environment, and error. So, ta-da. And as always, words. Words and cupcakes, that's how I roll. All right. So I know I rushed through this a little bit, but that's because I want to give you guys time to do your evaluations so I can win by getting more people to complete evaluations. So, questions?
So in the last example, there would be like two V matrix.
Yeah.
For each group.
Yep. Yep. It is a special case of a heterogeneous variance model where, yeah, there's separate G matrices and R matrices and therefore V matrices for each group. This is also what's known as a multiple group structural equation model. Same thing. All the parameters get to vary by group. Did you know you could do multiple group structural equation modeling in Proc Mixed? You know why? Because everything is a multi-level model, people. If you haven't learned that by now, that's your one take-home message. Everything is a multi-level model. Okay, other questions? All right, then here's the plan. I'm going to stop